Here's the title. This will definitely be algebraic topology. Operads and the bimodules. In topology. Right, so I'd like to thank the organizers for having invited me to come give this talk in this introductory workshop. And I must say that after the first day or day and a half of talks here, I was feeling deeply intimidated, because before coming this week, I only had the very vaguest idea of what a Grothendieck typology group was, and I had no idea what multiple zeta values were. And I realized that most people were giving talks in which they were trying to, or succeeding in, making connections among these different areas, operads, deformation theory, multiple zeta values, all this, so they're all putting it in one. I thought, what can I say? Well, fortunately, Dror Barnatan gave his talk yesterday morning, which gave me a little over a day to think about actually the fact that something Grothendieck-Teichmuller-like does show up in the context that I'm going to talk about. In one of the examples I'm going to talk about towards the end of this talk. So it's not exactly the same, but it's highly analogous. And I think it might be interesting to get together and talk about some possibilities here. But first I need to talk about what bimodules over operads are. So, in the spirit of the talks we've had on operads so far, I'm going to try to keep this quite elementary, particularly at the beginning, and draw some analogies. So I've thought a lot about modules over operads in various contexts for a number of years. And one thing I've noticed when I've talked about this to various people is that it can be hard for people to understand the difference between a module over an operad and a module over an algebra over an operad. So I want to make this distinction quite clear. And as Vladimir said this morning, it's really important when we're talking about operads to draw the analogies with what we can do when we're working over associative algebras. So I'm going to start with the baby case. I'm just going to talk about rings and modules over rings and bimodules over rings, and everybody knows all about this. So this is something where everybody can sit back and relax and say, yeah, I know this. And then we make a bit of a jump. But first we'll do the baby case.
So you'll put us asleep and then you will.
Then you go. Okay. So let's start with the homomorphism of rings. Now everybody knows what it means to be a module over a ring, and what I want to remind you of is that if you have a homomorphism of rings, then S inherits a natural R bimodule structure from using this phi. And everybody knows how to do this, but I'm going to write it down because this is what we're going to generalize. So this gives us an R bimodule structure on S in the way that everybody knows. That is to say, we start by looking at R tensor S. This is usual, just tensor product over Z. Then you do phi tensor identity into S tensor S, and you use the multiplication on S, right? And that's going to give you a left action of R on S. Let's call that lambda phi, for example. And on the other hand, S tensor R, identity tensor phi, S tensor S, use the multiplication on S, and then we have a right action, let's call it rho phi. And this is going to give us an actual bimodule structure for a number of reasons. First of all, because mu s is actually associative, we use the associativity of mu s in proving that, and we use the fact that phi is actually a homomorphism of rings. So the fact that mu s is associative plus the fact that phi is a homomorphism, together these are going to imply that lambda phi and rho phi are really actions. And then the associativity of mu is going to give us the fact that lambda and rho are compatible. Lambda is a map of right R modules, rho is a map of sorry, lambda is a map of right R modules, rho is a map of left R modules. So the associativity of mu implies that these two guys are compatible. That is to say, if we endow rho with these two structures, S with these two structures, then it's an R bimodule. Okay, so that's the kind of game we want to play now for operads. So the way I'm going to figure out what the right definition of a module over an operad is to say, well, I want, if I have a homomorphism of operads, for the target operad to be a module over the source operad. So now I'm going to the operad case, remembering, and I thank Vladimir very much for having discussed this morning so I don't have to do it, the fact that an operad is a monoid in the category of either symmetric or non-symmetric collections with respect to this monodal product that is denoted by a circle. So recall that an operad is nothing but a monoid in either collections or symmetric collections with respect to this symmetric product here. So what I'm going to do in the operad case is play exactly the same game with this circle product taking the place of the tensor product. So okay, so now let's suppose we're given a homomorphism of operads. So let phi from P to Q be a morphism of operads. And we're going to follow exactly this pattern and define a left action of P on Q and a right action of P on Q. So this is going to give us a left action of P on Q, like this. So we apply phi, and then we do identity in these components. So we end up in Q circle Q. We use the multiplication on the operad Q, and we end up in Q. And this is going to give us a lambda phi, which is going to be the left action of P on Q. And dually, we can put the P on the other side. Okay. Q circle Q, again using gamma Q. And we have a right action. A very important thing to notice here is that these two compositions have a very, very different nature. I mean, when we're looking at the action in the case of rings, there's no real difference between a left action and a right action of a ring on a ring. I mean, you can just use the symmetry homomorphism and the isomorphism, and there you go. Here, these are of very different nature. So let's consider the case of lambda phi, the left action. So what does it say we do? It says we take an operation, say, of arity k in P, and then k different operations in Q, and we put them all together and we get a new operation in Q. So we get something that looks like this. So for example, if, let's see, I'll try not to have only binary trees, and use some colors. There were colors here, here we go. Right, so suppose we have some ternary operation in P, right? And then what we can do is we can evaluate it in 3 different operations in Q. So let's see, that's probably not the best choice. That looks better. So we have then 3 operations, Q1, Q2, Q3, at least some of which are not binary. And where is this sent by lambda phi? Well, it's going to give us something in Q, but it's built up the following way. You have your operation in P, and then on top of that, you've glued little things from Q. So you have something like this, something like this, and something like this, and we end up with something that is in Q7. Sorry? I'm sorry, yes. All right, to be very precise. Thank you. Like this. All right? 1, 0.
You should add gamma of that too. Yeah,
I refuse.
Okay, you can.
This is all symbolic, right? Okay, how does rho phi look? So, we'll just sort of switch the colors, right? So, this time we'll have one operation coming from Q, and then a bunch of operations coming from P. Like this. Let's see, I better not forget the phi's this time. So then you get a tree that looks like this. So you have your one guy from Q, and
this
then
is again Q, not something different.
this is really Q, yes. And this one is phi of P1, phi of P2, and phi of P3. With a gamma that's out there for Bruno. And again gives us something in Q7. But you see, on the one hand, this one takes one input from Q and gives you something else in Q. This thing is sort of linear in the Q variable. This one, on the other hand, is highly non-linear in the Q variable. You stick a bunch of different guys from Q in. And this makes working with left modules sometimes much more complicated than working with right modules.
Sorry, say again, why non-linear? What in what way?
Because you're putting
It's
in,
cubic in.
you're putting, this particular operation is cubic in
okay,
Q.
okay.
Yeah. The point is this is a highly non-symmetric situation. Left modules and right modules behave very differently from each other. And one of the points of this talk is going to be really to try to make that difference as clear as possible and to give you examples of both kinds of constructions so you can really see the difference between the two.
Is it worth mentioning that there is a linear version on the left?
I am going to. It will be mentioned. And it's worth mentioning, yes, but not now. Or not yet. Okay. So let's generalize this. Let me just write down the formal definition so that so generalizing so that this structure becomes that of a P bimodule. So these morphisms P bimodule. So this is, I'm going to formulate definitions so that this guy fits definitions, right? So, a collection or a symmetric collection, whichever you prefer, it's called X, so we're sure that it's not necessarily an operad, is, or sorry, this is not well formulated. This is the right way. A left P module, where P is an operad, is a collection or symmetric collection together with a morphism of collections appropriately symmetric collections if that's what you have, lambda from pre-circle X to X such that, well, it's going to has to be an action. So how do we write down the action diagram? Well, we're very happy that the composition product circle is an associative monoidal product, so I can just sort of forget the parentheses here. So going from here, we can either apply the gamma for P and the identity on X, or we can apply the identity on P and lambda, and again lambda, so that I end up in X, and this thing must commute. So commutes, and there's a unit condition. I'll drop it over here. Because we have this very special element. This element has been called I this week in level 1 of the Operad. So we have a map from X into P circle X. It's just taking some X in arity N and sending it to what you could write as I circle X or something like that. Whatever notation you want to use. So it just puts it in using the identity element. And then you can apply lambda. And so acting by the unit element should just be the identity. So it's an action with respect to this monoidal product. Similarly, let me just write it down, maybe not in quite as much detail. A right P module. So it's a collection X plus now morphism of collections from X circle P to X such that the appropriate diagram commutes. So let's see. I'm using the diagram. I'm going to make a mistake. X circle P circle P. And here we have rho. And there's a unit diagram as well. Some sort of unit morphism there. Rho, this should be the identity. And then the idea of a bimodule is, of course, that you have left and right actions, not necessarily the same operad. And it's going to be important to be able to vary like that, in fact, that are compatible. So let me just write that down so that everything is clearly defined. Oops. Microphones are always a pain. So. Right, so last part of the definition. So if you have a left P action and a right Q action, so these are both actions, so they both satisfy these definitions.
Not Q but P.
Sorry?
Not Q but P.
No, I want Q.
Okay. Two different algebras.
Yes, absolutely. You get very interesting information from having two different things. So, in that case, you have that X together with lambda and rho is a PQ bimodule if, well, the obvious diagram commutes. That is to say, So we can either act on the right by Q or on the left by P. You can do them in the order we want, and it doesn't make any difference. P circle X. So this should commute as well. So actually it's compatible, you can do them in the order you want. So this just generalizes in the most obvious way what we're used to doing for modules and bimodules over rings.
So, but it just depends on the fact that you have a monoidal category.
That's right. That's right.
No special property of this.
No special property. I just wanted to make very explicit what it means in this category. Absolutely. Yeah, it's just the notion of modules and bimodules in a monoidal category. Absolutely. So now let's start on some examples. First, I'm just going to do some elementary examples to show how these notions of modules and bimodules are related to things we've already seen this week. So, and then give more interesting examples to say why we should care about generalizing beyond the things we've already seen. So, the point of these first examples I'm going to give is that you already know, at least if you've been paying attention this week, you already know many examples of left modules. So here's the first example of a left module that you already know. So we're going to let P be an operad. Suppose now that A is a P algebra. And I'm going to build up a collection which is going to be A in arity 0 and 0 everywhere else. So here let's suppose that we're working with operads of chain complexes or something like this. Otherwise we can be taking just a base point empty set. So I'll call it Z of A because I'm putting A in level 0. So it's going to be the sequence or collection A, 0, 0, 0, like this.
You begin by degree 1.
Sorry?
You
begin by degree 0.
Arity.
Arity. Yeah, let's call it arity, because that's the right word. Definitely an arity 0. Okay, then this Z of A is actually a left P module. To write down what it means. So what it means for something to be a left P module, let's just write it out a little bit so you can see what's going on. Okay, so if I look at, but this morning, Vladimir cheated a little. He was talking about collections that had nothing in degree 0. Well, it's not too hard to extend to something where you actually have something in degree 0. So let's look at what we get in degree 0 here. So first of all, let me observe that if I have a match from here to here, all that really counts is what's happening in arity 0, because what I have in higher arity is just 0. There's nothing going on. So only arity 0 shows up, really, because everything else is 0. So let's calculate this. So this thing here, because Z of A is concentrated in arity 0, is nothing other than the sum. Okay, I'm going to suppose that the operad has nothing in arity 0, just to make things. You win, Vladimir. Okay, let's just to keep things a little more simple. So we'll assume that P of 0 is 0. Then this, for n greater than 1, it's just going to be this considered with A and times. Because what are you getting it should be Pn where you have n times z of a arity 0, which is just a tensor n. So having a map from p circle z of a arity 0 to z of a is the same as having a map from this direct sum of Pn tensor n power to a.
But your operator is non-symmetric now.
Yes.
Well, if it's symmetric, you
If it's
just
symmetric,
change
I'll
the
put in
tensor
this-
product, that's all.
Yeah, I just put in this, so assume non-symmetric, just to keep things easy. I mean, one can do this in the symmetric context
Of
as well,
course.
but I am
Change the
writing,
tensor product, that's all.
yeah.
Yeah.
But do you have a good reason why you ask P0 to P0? I mean, this works very well.
No,
I wanted to remove 1 point from Vladimir. Yes.
if you want to have P0 different from 0, that's fine. It's not going to change this calculation. Okay, so you end up with something like this. So it's really, what you're getting is a structure of a P algebra on A. It's exactly the same thing. So let's generalize a little bit. Well, generalize and specialize at the same time, actually. Since we haven't yet seen the notion of a module over an algebra over an operad, except in the case that everybody knows, which is when the operad is the associative operad, I'm going to restrict to that case, but then push a little bit further.
Sorry, can I ask a very stupid question? For those of us who have never seen the construction before, could you remind us of the definition of P circle Q for any operad?
Sure.
I'm just a bit confused about the arity 0
Sure.
account. And the count.
It's not a stupid.
Is not.
All my questions are
No, there's no stupid question.
So P circle Q in arity, and I'm going to write the non-symmetric version just for simplicity. The direct sum over, do I have to take P of 0? I mean, I'm going to take P of 0 to be 0 again, just to keep things.
Oh yeah, but that was okay.
Yeah. Let's see. We take over sequences n1 up to nk, such that the sum of the ni's is equal to n of qn1 okay? So that if we're going to get 0 here, all of these guys have to be 0. Okay? So it's important, it's a good question, because it's important to understand this example, particularly since I'm now going to generalize it. So let's move down to a situation where we have A, which is an associative algebra. Just an algebra in the usual sense of the word. And M, an A module, and everybody knows what that means. Actually, an A bimodule. So this goes back to elementary ring theory. Now we're going to consider the following sequence. So let's see, I should probably give it a name. Which way does it go? Like this, right? So we have a sequence that is A in arity 0, M in arity 1, and 0 everywhere after that. This is now a left as module. So let's see what happens in arity 0. Well, arity 0 is basically is the same as the previous case. So well, there it's only A that shows up again. So that's, again, the direct sum. I'm taking non-unital associative algebras. Like this. So there we just got this. So again, in arity 0, all you're seeing is the multiplicative structure of the algebra. Okay, so you just have this. Because this is exactly this thing evaluated in level 0. Now what happens in level 1? Well, let's check. First of all, the level 1, arity 1 of this sequence is M. And what's arity 1 of this thing? Well, let's see. If I go back to this formula that Francis asked me to write on the board, so if I put in S here and for Q I put in this semi-direct product thing, then if I'm going to get n to be 1, then I have to look at sequences where all of the ni's are 0 except for 1. That means that the kinds of things that are showing up in arity 1 are some n's like as follows.
Why does your semi-direct product stop? Is that
It won't in the next example.
We will get A infinity.
So let's see. Let's look at what happens in the other case. We look at this thing in arity 1. What do we get? Well, again, we have all of these terms tensored with. And now we have various possibilities of sticking just one copy of M in. So it looks like things like A tensor I, tensor M, tensor A, tensor N minus I minus 1. N minus 1. It has to be at least 1, right? No, M can be all the way on that side. That's right. Yeah, equals 0. It's ones that look like that. And so what's going on when you have the map in arity 1 is you're using then the bimodule structure, the left and right actions of A on M to define this multiplication. So the map like this to this thing in arity 1 is built from rather, let's see, left and right actions of A on M. Okay. And then after that, there's nothing going on. Since this guy in higher arity is 0.
Everything is 0.
Yeah. Okay.
So, may I have a question?
Yes.
One can view M by module by simply saying that you have a module structure, an associative algebra structure on A plus M.
Yes, that's the
So,
same.
why not put directly A plus M and put M in arity 0?
Because of the next example.
Of course, it is the same.
This is, it's just because this is a sort of a natural extension of the idea. I mean, you're right, doing a square zero, this is doing a square zero extension here. But now, with the next example, we'll see why I did this, because then it generalizes. Okay? Because I like, when I'm looking at square zero extensions, I like to think of the two parts sort of as living in different degrees.
Can I just say that the proof that
an AS module in that way is exactly a bimodule, is exactly the proof I gave, saying that the Operads AS was modeling the toxicity variable. It's exactly the same.
Thank you.
Yes.
I didn't catch what you said.
You take the Operads AS, one guy per RET. And then I said, okay, what are algebras over that? You know, I did a small computation.
Yeah.
It's exactly the same computation, putting A's and M's.
So it's nice to see the same computation showing up in different places. So, now let's think more generally about left modules of the associative operad. And maybe I'll leave the details as an exercise. More generally, if you have a left module of the associative operad, if and only if, when you take this, you take your collection here, and I'm going to look at it as a graded object, a graded vector space. And there's a tensor product, a symmetric tensor product, defined on graded vector space, which is the graded tensor product. And it turns out that being a left module of the associative operad is exactly the same as being a monoid, an AS algebra, with respect to that graded structure. And that's exactly what's going on in this special example of the square zero extension. If and only if X is, or, well, is a graded monoid, that is to say, an AS algebra with respect to the graded tensor product. Of collections. So somehow, in going from algebras to left modules, all we've done is go to two-dimensional, or sort of vertical algebras now. So, with graded tensor product, let's call it circle dot, just to distinguish it from the other one. So just, again, in the non-symmetric case, this thing in level n is the direct sum k equals 0 to n xk. N minus k, and in the symmetric case, you throw in symmetric actions. So it's the usual graded product. So this really tells us that left models of the associative operad, these are things we already know. They're not so different. And this generalizes as well to other operads.
So it's a graded algebra.
Yes, but now it's graded. Before, so this is going from ungraded to graded when you do this. I haven't said anything about right modules yet, so let me just say a little word about that. There's no kind of hook or something? Sometimes it's bad to be a little short. I can't make a move.
Least first.
Yeah.
I
Yeah,
believe
let me do
the
that.
first one and-
Good idea. That's easier. Thank you. All right, so one more example, elementary example. Just this is something that makes a right module structure show up. So if left modules are about algebras, right modules are about, are you as bad as my Swiss classes? Co-algebras. Aha. So let's see what I mean by that. So, well, let P be an operad. And I'm going to consider a co-algebra over this operad. People usually think about co-algebras over co-operads, but there's a coherent way to talk about co-algebras over operads as well, in the following sense. What do I mean by that? You have some collection of maps where P is now co-acting on C instead of acting on an A. That is to say, for every n, you have some map from C tensor Pn into C tensor n, plus conditions. So that it really takes into account the multiplicative structure of P. Okay? So it turns out, let's see, now I need to go up. So it turns out, by a similar sort of computation, this is how to talk about coalgebras without dualizing anything. That now look at the sequence that I like to call T of C, because it's the tensor collection. So the tensor collection, let's see, and I always, well, okay, I put a 0 there. And then C, and then C tensor 2, and then C tensor 3, and so on. So TC. And I already N is C tensor N.
How do you use the gamma multiplication in Pn for defining the structure, the relations between these?
Here?
Yeah.
Well, you have C tensor Pn, tensor maybe Pik up to Pi1 up to Pin. And then you can first coact and you get C tensor n times. And then on the first copy, Pi1 acts, and the second copy, Pi.
When you have an ordinary coalgebra with simply C into C tensors, you can extend it to a collection. Pn in this case is just one-dimensional, and you have iterated coproduct, which is familiar.
Right,
and it satisfies some kind of associativity or
That's right.
co-associativity.
So you can think about co-associative coalgebras this way, absolutely. Using the associative algebra. Okay.
If P as C is simply a co-associative coalgebra.
Exactly. So, right, so let me just, you can take C. That's an example that's well known. Okay, so the exercise, so I can get on to more interesting things, is the following. That this sequence now has two structures. It's a left module and a right module. It's a bimodule. And here are its structures. It's a left module over the associative operad because there's a multiplicative structure on the sequence. It just comes from concatenation, right? So it's a left as module because it's a graded monoid. And it's also a right as module, and that's coming from this co-multiplicative structure. So oh, sorry, the right structure is actually coming from P, so it's so that's a fairly interesting example. So this is an exercise. Okay. So now I'm going to talk about some examples that are...
So as bimodule
is the same thing as a... well, in this case, if we were as bimodule, so you have this tensor sequence, which is an as bimodule, but it's the same thing as having this co-associative coalgebra structure on C.
In case you have at the same time an as module and an as bimodule, is it a bialgebra? The compatibility, the commutativity?
No, that was my question.
No, because there's no, this does not imply that there's any multiplicative structure on C. It's a multiplicative structure on the whole sequence.
Yeah, but in the case of TC, but I'm asking if you have a module of a left module and a right module at the same time. So is this by algebra?
No, because...
No, it's a difference between when you had a coalgebra as an operator co-opera.
You have to sort of keep track of what the context is.
You need operator.
Okay, so some topological examples. So just to use some of the elementary examples that I just gave and then recall some things we've already seen this week. So if we start with that, then for example, was it Bruno, I guess, who said that n-fold loop space is a Dn algebra, right? So if I look at the sequence, so if I pick some base points, so here we go, I have base space, I look at the n-fold loop space with respect to the base space, and then I take so I'm looking at pointed space with a point anywhere, that's my 0. This thing is a Dn module, where Dn was this operad of little n disks, because this guy is simply a Dn algebra. So I'm not saying anything, it's just applying one of the previous examples. Let's see, what else I want to talk about? All right, here's one. So if I take the chains on the topological space, let's see, yes. If I take the chains on topological space, I have a co-associative coalgebra, and so this sequence, where I take singular chains, so 0, this one, in fact, it has much more structure than that. But that's all we'll say for the time being. It's actually a right E infinity model. But we haven't talked about E infinity yet, so I'm not going to. There's one example coming from an important operad morphism in this context. And which may show up another example later if I have time to get there. So. So we can, I mean, maybe we have to make a good choice, maybe not. If m is less than n, then there's a natural operad morphism from the little m disk operad to the little n disk operad. And in fact, so this makes the little n disk operad into a bimodule of the little m disk operad. And this structure is in fact very important for certain calculations in geometric topology. So. So this may show up in a little while, if I have time. Okay.
Excuse me, how do you map D1 and D2?
So let's see. If I'm thinking, so I'm thinking about, I'm taking disks with a framing, right? And so I'm thinking about, I fixed the unit disk, or positioned in the origin around the plane. And for D2, sorry, D1, oh, so D1 is just the interval, right? And so you just map that in as the diameter of the circle. And you have intervals between intervals that you blow up to make little circles. There's a, you see, you have your intervals and you make them into little circles.
So the disks line up on a straight line, right?
Right, but you can do it for disks as well, just by choosing how you blow up.
Rotating.
Yeah, exactly.
Yeah.
Rotating, that's the word.
Sometimes it's better to replace a little disk by the little cube
That's right. That's
when
right.
you have such product.
Yes. But since we've been talking about little disks so far, you can do it with the disks.
The cube is better.
Okay. So now I want to talk
Cubic homology was good to foresee.
Oh, cubic homology is great for many things. Many things. So now I want to talk about an example of a really important bimodal structure that shows up in topology, which is where I think maybe there's some sort of analogous thing to the Grothendieck-Teichmüller construction that could be worth looking at. It's probably a very hard problem, but I think it's worth setting up the framework probably. So this has to do with Goodwin's functor calculus. Which in my opinion is one of the really wonderful things that happened in algebraic topology in the last 20 years or so. Sort of a calculus of functors, which is a way of breaking up functors into polynomial bits and then gluing them back together to try to get the functor again. Really, the idea is to make a sort of a Taylor series of a functor. So here's the idea. So we start with a functor. I mean, there are many variants on this. I'm just going to talk about the most unstable variant, which is functors from pointed topological spaces to pointed topological spaces. And I want this functor to be a homotopy functor in the very elementary sense of preserving weak equivalences. So many nice functors like that. And for example, the identity functor, which actually turns out to be really interesting to study in this context. So what's the idea? So we want to do an approximation of this functor f. So we first want to approximate f by what are known as polynomial or excisive functors of higher and higher degree. So there are various notions of the word polynomial, or senses for the word polynomial with respect to functors, as Christine well knows, for example. And once you have these polynomial approximations, they're actually going to build a tower that will approximate the... and then what we want to do is we're going to in fact decompose each of the polynomial pieces into actually homogeneous pieces, pieces of like x to the nth power. And the hope is then to be able to reconstruct your original functor from these pieces. So, more formally, what's going on? So there was a series of 3 articles by Tom Goodwillie in the 1990s, maybe the last one was actually published after the turn of the century, in which he developed all this theory. So he showed that for every n, first of all, 2 things, for every n greater than or equal to 0, there is a functor which he called n excisive, but you can think of as being polynomial of degree n in some appropriate homotopic sense. So there exists an n excisive functor, which is also a functor from pointed spaces to pointed spaces.
So f is given.
F is given, so given f. Right? So this n excisive functor, technically it's a functor that takes strongly co-Cartesian n cubes to Cartesian n cubes, but it's the appropriate notion of polynomial of degree n in this context. And natural transformations, let's call them In from f to Pnf. And a natural transformation from the nth approximation to the n minus first, which is compatible with these comparison maps with respect to f, so such that the obvious thing commutes.
So Pnf is viewed as a better approximation than Pn minus 1.
Yes, that's right. It's an increasingly good approximation of f, like this. And but we can compare them all the way along the tower. And it also has a universal property. Anytime I have a natural transformation from f to an n excisive functor, it factors through Pnf. So it's universal with respect to, in this context. So for all g from f to g, with g n excisive, there's a unique factorization through which it commutes.
Unique or unique of two models?
Unique.
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 Strong.
Strong, absolutely. So it really has a universal property. So that's the first thing. And I'll put the second one over here. So we're interested in what's happening as we climb up this tower from Pn minus 1 to Pn and so on. And the way we do that as homotopy theorists is to calculate the homotopy fiber, which is the homotopy theoretic kernel of this map Pn. And we examine those things. So let's let dn of f be the homotopy fiber so it tells you what the difference between these two functors is. So when I say this, this means we're calculating object by object. We fix a space and then we calculate the homotopy fiber when we evaluate this at a certain space. So this is a functor also from spaces to spaces. And what Goodwin showed was the following. There exists, oh, here comes a scary word, a spectrum. So a spectrum is one of these series of spaces which have a map from the suspension of the nth space to the n plus first. I mean, that's the rough idea. These are the objects that stable homotopy theorists study. It's stabilization of of topological spaces. So the spectrum, dn of f.
So sorry, does the n here is the n of the tower of for the spectrum, or it's something different? This dnf is itself a spectrum.
It is itself a spectrum.
So
Its name is dn of f. That's right.
An index, not
Yeah, it's just telling you that it's the nth piece here. Okay, and with the sigma n action, such that in order to calculate dnf of x, what we do is we take the smash product, which is the appropriate monoidal product for spectra, with the iterated, we're working with pointed spaces, so we can always smashes. So that's the appropriate monodal structure for pointed spaces. We can smash together a spectrum and a bunch of spaces, and we're going to take the homotopy orbits of this. So we're taking the homotopy co-invariance of the sigma in action, because it acts here and it acts here. And we look at the diagonal action and we take the homotopy orbits.
When you say homotopy fiber, it is well defined or up to homotopy?
It's up to homotopy. This is really up to homotopy. Yeah. Sorry. I sort of vary between working in the homotopy category.
No, because we insisted before.
Yeah, absolutely. Absolutely.
Not up to homotopy.
No, this is no. Okay. So let me just draw the big picture. So we have a tower, and P0 of f is just, in fact, it's the constant functor at the base point. P1f make that n-1. So we have this nice sort of graded sort of filtration of f. Huh? And here we have dn-1 of f, dn of f, etc. So let's see, a bit of terminology and some remarks here. So this is called the Taylor tower. Which has been expanded at just the one pointed set. So we're looking at these as successive polynomial approximations to f. And this thing is called the nth layer. And this spectrum, del n f, we have here, we call it the nth coefficient. And I'd just like to draw your attention to a couple of things here. To look at the analogy with Taylor series. So just to...
So,
yes.
so there's something slightly wrong in that last statement, because the left-hand side is a space, isn't it? Whereas the right-hand side is a spectrum. Do you mean the...
Where? Here? Oh, sorry.
You mean omega infinity of that?
Yes, thank you. Thank you. What this means when I take omega infinity is that here I have a spectrum. I take the zeroth space of the spectrum. That's all I'm doing. Sorry, thank you. Thank you for that. Thank you. Okay, so some remarks. And then I'll get to the connection with Operads. We're almost there. So we say the tower converges at x if, when we take the homotopy limit of this tower, so we do some sort of fiber replacement and we take the limit, if f of x is equivalent to the homotopy limit of the tower. And convergence is usually related to the connectivity of x. Usually if x is highly enough connected, the tower will actually converge. And this piece, it turns out, is actually what we would call homogeneous. There's a technical definition of what it means to be homogeneous. This is homogeneous of degree n. Let's see. It's short. Oh, I just wanted to mention the analogy between the form of this nth layer and the nth coefficient of a Taylor series of some function f expanded at 0, which of course is the nth derivative of f evaluated at 0 divided by n factorial. This business of taking the co-invariance for sigma n action is like dividing out by n factorial. So that's a very nice analogy. The last thing is that maybe surprisingly, the Taylor tower of the identity functor is actually highly non-trivial. I mean, usually think the identity should be like 1, you take its derivatives, they're all 0. Not at all. If you think about what it means to be even 1 excisive, you'd have to have a functor that was taking pullbacks to pushouts. Sorry, pushouts to pullbacks, which is not at all the case of the identity functor. So the Taylor tower of the identity is highly non-trivial. In fact, very interesting. And it does converge. Or at least for simply connected spaces. So, still don't have operads in the picture, but here they come. There's a theorem due to Aron and Ching which says that there's a chain rule for these coefficients. So if I let del star of f be equal to the collection of the dn of f's, that's notation, then for any functors f and g, you have a natural map from the composition. These guys are now collections, even symmetric collections. You can take the composition product of symmetric collections, and you have a natural map from this composition product of symmetric collections to delta star, lower star, sorry.
You need, of course, the spectra of symmetric monoidal category.
Sorry?
You need the spectra of monoidal category.
Yeah.
Symmetric monoidal
Yeah,
category.
yeah. Yeah, you need a symmetric. You need a
So you
symmetric.
can talk about operads in the category of spectra.
Right.
Yeah.
That's right. Because these guys are. This is now a collection of spectra, a symmetric collection of spectra, and I choose some nice category of spectra, which is monoidal. There are lots of nice examples, lots of nice models one can choose, and the corollary one gets.
What kind of property for this map?
Sorry?
It's not an equivalence.
No,
in any
but
sense.
when you then take the co-equalizer, well, so from this you can see, just a second,
Okay.
2 more steps. So corollary is that since the identity circle the identity is the identity, this gives us is an operad in spectra.
A category of
Right. So collections of spectra. It's an operad is pieces of spectra. And
module.
is a bimodal. So, what I believe that Aron and Ching have proved is that when you take the homotopy co-equalizer over the action on the right and the left of this operad on here, then you're going to get something that's like an equivalence. So it's not usually an equivalence here, but all we need to get this is to have a map. Right, so now, so what does this have to do with Grothendieckteilchen? Maybe nothing, but let's take a look. Driven by analogies. So for having given a nice explanation yesterday.
Can I make a comment about something you said at the beginning?
Yes?
You were intimidated?
Very. Okay, so let's go. So we need one of these B, C, ASSO things, right? So, I mean, if you look at these towers, right? These towers are giving us something that looks like an increasing filtration of F. And I mean, it's highly analogous to the tower you would get by taking quotients by increasing powers of the augmentation ideal. It's a very, very strong analogy there. And so I would propose to set things up as follows. Your B, now we're working with in homotopy theory, so we're going to have to take this would be the homotopy category, so I'm going to quotient out by or localize with respect to the weak equivalences of Taylor towers of these homotopy functors. So these functors that send weak equivalences to weak equivalences. Okay? And then the Bm would be the category of towers that are truncated at level m. And B hat is probably the homotopy category of limits, or homotopy limits of Taylor towers. Which, for highly connected up spaces, gives you most of the functors back in the end. Right. So what's the other picture? Well, what Dror was talking about yesterday, he said, look at the filtration quotients. That's what we have to look at. So the best way to look at that thing, I think, is to take C to be the category, or the homotopy category, of bimodules over this operad, because this sequence of coefficients is a bimodule of this operad, and that is the essential structure that you have. You may need some more structure based on some things that Aron and Ching have done in this sort of spectral context, plus perhaps Ecole algebra structure. A certain comonad that I don't have any time to explain, but this is something that comes up in a sort of analogous situation for spectra, so I think we probably need something like that here, but this is the main thing. And here you'd sort of take a truncated version of this thing, and here you take some sort of homotopy limit. And then you would have associated GT, GRT, and ASSO. And one thing that is a big, big question, huge question in homotopy calculus, is how can you recover the functor itself from its derivatives from these coefficients. So if you could say something about, maybe what extra structure you need to have on this category so that you would actually get an equivalence of these homotopy categories, that would tell you a whole lot about when you can recover a functor, not just from its Taylor tower, but from the derivatives, from the coefficients in the Taylor tower. So this problem is actually of fundamental importance. And so if you could play the kind of game that George talked about yesterday, where you know that you have successive surjections from ASO M to ASO M minus 1, and so you can do a recursive construction of an equivalence. That could be extremely important and extremely interesting. So it's not the same GT, I don't think so, but it's something very interesting and worth thinking about, I believe. Okay, sorry for going way over.
Is there any question?
You're proposing the analog of Verone and Chang's result for spectra, and so they understand what you need to recover
That's right.
the whole tower. So you want to know the analog for spaces.
That's right, I want to know the analog for spaces, Verone and Ching's result for spectra. Yes.
And do you think there would be a map? Another comment that Kathryn probably knows much better than I do is that the derivatives of the identity are the operad for homotopy nilpotent groups. So if you pass to pi naught, you get the nilpotent operad telling you what operations you have for nilpotent groups. And if you take this Taylor tower of the identity, you get something like the completion with respect to the lower central series. So you're picking up things like the lower central series, the associated tower with the lower central series of the Ecole homotopy type of moduli spaces. So it would be nice if there was more than just a lower central series connection, if there was a map from something like this to GT to find out if there was extra arithmetic information in GT, it's supposed to look like the Galois group of Q, and there's no Galois group of Q there, but to sort of filter out what's general sort of lower central series versus n-excisive, these are sort of the same. That pile of algebra versus real number theory. And if you could separate those out, that would probably make the number theory easier. So I really like your suggestion, but it would be great to have some map, one way or the other.
From what?
From your GT to another GT, or some diagonals of maps.
Yeah. That sounds great. I think that, there's, I don't know where to start looking, but here we've got a group of people who have all sorts of competencies, so maybe we can figure it out. That's a very good remark, definitely.
A very quick remark, on the sort of much earlier part of the talk. An example of left and right modules. So basically, if you consider the category of non-symmetric collections with the shuffle composition product and study left and right modules over the associative operad viewed as a shuffle operad, then it is related to various questions of combinatorics of permutations. Left modules are related on looking at relative order of consecutive subsequences in the permutation, and right modules are related to combinatorics of relative orders of subsequences, not necessarily subwords. So that shows the difference between left and right, and also using homological algebra for shuffle operads, you can actually answer some questions on combinatorics and permutations that people from combinatorics didn't know how to answer.
Hey, did I give credit to Biederman and Dwyer when I made that comment?
No.
Sorry, it's Biederman and
They
Dwyer.
can't hear you, so yes.
But then you guys know where to look, and
Just one question. Here you apply these techniques only on the morphisms of functors of the topological category, but could there be a similar construction for morphism between different categories?
Absolutely. Absolutely. You just need to have some kind of homotopy theory in the categories.
Because I had in mind what was explained in because there was the more abstract description of using these functors omega and Bethe homology. And so maybe there you could also have this kind of towers, and then maybe you could filter or decompose the automorphism groups thanks to this technique.
Yeah, great idea.
Any new idea? Give as much as ideas as you want. You have 4 months to solve that.
I have a question. So is there a nice example of a bimodule that's more natural? So you saw yesterday that we have this way of taking a symmetric sequence and taking W and versus just taking that operad. So is there a nice example of a need for that, of the form, I have this module that's naturally a module over the W version, but it wouldn't be on the nose?
You can have sort of up to homotopy modules as well. I mean that could be a generalization of up to homotopy algebras, and be a natural generalization of that. It can be very useful to be working over, because that operad has some very, very nice properties.
The W.
The W one, yes. That so that I've seen some situations where it was really useful to be working with that particular operad.
I'd really enjoy an example.
Okay. Yeah. Maybe.
Can you name it or something?
Well, no, but I mean it's more like a context than a specific example. And we'll see whether that's what you have in mind. But yeah, I'm happy to talk to that.
Any therapies by module over the Bowman flock. Trivial example if you.
But that's even without the homotopy version. I wanted an example where you had a sort of natural module structure over the homotopy version, and then you'd have to work real hard to push it down over the non-homotopy version, because that would be justification for why we should keep track of all those lovely homotopies.
Any other questions? Mark? Okay, thank you again.